Hi guys, and welcome back to our video series. So far we've been looking at reversible and irreversible reactions and what that actually means. And now it's time to look at that with respect to equilibrium. So what is equilibrium? There's actually two types of equilibrium. We've got static equilibrium and dynamic equilibrium. And today we're going to find out just what the difference between the two is. Let's go. Okay, so our learning intention for today's lesson is to explain the difference between static and dynamic equilibrium, and also how do we know when that point of equilibrium has been reached. So I suppose the first thing we really need to do is look at, well, what exactly is equilibrium? So our equilibrium is that point when the concentrations of both the reactants and the products are constant. So their ratio doesn't vary. So that's where it's important that we look at the mole ratios on the reactants and the product side of the equation. So when most people think of equilibrium, they think of a balance, like a seesaw, where both sides of the equation or both sides of the seesaw are balanced. So what's happening there is the forward reaction is happening at the same pace as that of the reverse reaction. So many of the reactions you've looked at to date have been static equilibrium. And when we do that, we often think of a reaction that's just going in one direction, and the reactants continue to produce the products until all the reactants or the limiting reagent has been used up. Another type of equilibrium is dynamic equilibrium. And what's happening in a dynamic equilibrium system is that as the reactants are forming the products, those products are now reacting and going back and forming the reactants again. So when the reaction actually appears complete and has reached equilibrium, there's a mix of both reactants and products in the system. Now, if you have a look in this diagram here, you can see that there is that transfer between our movement of the particles of our reactants into our products. At that point of equilibrium, there's a mixture of both. So dynamic equilibrium is actually an example of a system at steady state. So remember, steady state is those standard conditions. Now all those systems have those constant properties, so temperature, pressure, volume, etc. So all of our systems in a dynamic equilibrium must be in a steady state, but that doesn't mean all steady state systems are in equilibrium. So we'll talk about this a little bit further in class. Now when we have an equilibrium system occurring, you can see in the diagram here, at the beginning of the reaction we have all reactants and initially no products. As the reaction starts to occur and progress, we have some of our reactants converted into those products. So initially the forward reaction producing the products is quite high, which you can see in the second part of the graph there, where the rate of the forward reaction is quite high. As we're forming some of the products, we start to get the products or the reverse reaction starting to increase. In this diagram here, you can see that we are producing more products. So our reactants are reducing, the concentration of the reactants are reducing, and the concentration of the products is increasing. And you can also see then that the forward reaction is still occurring, but the reverse reaction's rate is also increasing as they are converting into the reactants again. And as our reaction comes to completion, it doesn't mean that the concentration of the products has to equal the concentration of the products, but you'll notice that the forward reaction equals the rate of the reverse reaction. And it's now said to have achieved equilibrium. So therefore the rate of the forward reaction will decrease as the concentration of the reactants decrease, and the rate of the reverse reaction will increase as the concentration of the products increase. So an example of this is nitrogen dioxide converting into dinitrogen tetraoxide. So when we have our initial reaction, our initial nitrogen dioxide is actually colorless, and our dinitrogen tetraoxide is a dark kind of browny color. And so as the reaction progresses, we will see that nitrogen or dinitrogen tetraoxide being produced and then it moving back. And once equilibrium is achieved, we'll get a light brown colour. So when this actually occurs, the reaction hasn't stopped. It's just reached a point of equilibrium where the rate of producing the products is equal to that of the products producing the reactants, and that equilibrium has been achieved. You won't notice any visible difference once this happens, but at the microscopic particle level, that reaction is still occurring. So just in summary, when we have a reaction that is at equilibrium, the forward and the reverse rates are now occurring at the same rate, but this does not mean the concentrations are the same. An equilibrium will only occur in our closed system. So if particles can escape, then it won't reach that equilibrium. Now this doesn't mean it's got to have a lid on top. If it's a gas produced, then a gas can escape into the environment, so obviously we would close that one. But if no reaction at the gaseous form is occurring, then nothing is lost or destroyed. What I'd like you to do now is watch this video